talk a little bit about concepts in information theory. But first off, what is information? One definition of information could be that it is something that decreases uncertainty. So how much does knowing a piece of information decrease the uncertainty about a particular event? Here's sort of an example. What if I were to ask you, is it raining in Seattle at this very minute? Now, knowing what Seattle is like, there might be a lot of uncertainty. If you look at the weather forecast of Seattle, there's some chance of rain every day. You don't know if it's raining at this very particular minute or not. So you're actually going to learn some information if I called my friend in Seattle and she said it was raining or was not raining. There was some uncertainty there and it got cleared up. But if I were to ask you, is it raining in Phoenix? The answer is most certainly not. It's in a desert and every day kind of looks like this. So if I call my other friend in Phoenix and they say it's not raining in Phoenix, then that doesn't really surprise me at all. So the information about Seattle cleared up more uncertainty than the information about Phoenix. So therefore it gave me more information that I did not have before, if that makes sense. But the key to quantifying information is actually to quantify how much uncertainty was cleared up. So if you want to know that, you have to think about the possible values that a particular random variable could take. If the random variable can take a lot of different values with high probabilities or probabilities that are kind of spread out, then there's a lot of uncertainty about the variable. But on the other hand, if the variable is very peaky, like this blue Gaussian distribution, where it usually takes on this value, then there's little uncertainty about the variable. So this is definitely a function of the probability distribution of the random variable. So more spread out, wider distributions have more uncertainty and therefore more information. But peakier distributions have less uncertainty, therefore less information. So if we want to think about what are the desired properties that a quantification of this kind of information would have, there's some immediate properties that are pretty intuitive that you'd want. If there's two completely independent events, you get some information from this independent event, you get some information from this independent event, then you get twice as much information because there's no kind of overlapping information. They're completely independent events. On the other hand, if you have two things that are dependent, then it'll be less than the sum. Another property is positivity, which means that all information is positive or zero. There's nothing that gives you negative information, or there's no such thing as a negative surprise. Either you're surprised or not. Certainty is another property that you want. If something actually happened, you actually see it happening, then there's no surprise left. You already know the result. And one other property that you might want to think of is permutation invariance. So if the odds of the events were all switched around, you still have the same amount of uncertainty. So if you had a loaded die, which often comes up 1, and the rest come up with an even probability, but I just switched the labels, and now the loaded die gives you 2 more frequently, then there's still the same amount of uncertainty. And the very last property that you could think that you want or you desire is that if you have a uniform distribution with m outcomes, then that should have less uncertainty than a uniform distribution with m plus 1 outcomes. So a fair coin should have less information than a fair die. So if you actually put all of these properties together, you actually get only one function that meets these constraints, and that is actually the log function. So if you just take, for example, this additivity constraint, that if you have two independent events occurring, and what is the information you gain from those, can you just add up the amount of information? This identity very strongly refers to logs, because log of a times b is log of a plus log of b. And so you can actually take the derivative and set this equal to 0, and this differential equation actually leads you to a function that has the form k log of u. And actually, Shannon entropy follows exactly this format. Shannon entropy measures information or the reduction in uncertainty as the probability of some event or probability of some outcome times the log of the probability of that outcome with a negative sign to give positive values. So under this definition, the fair coin has probability of heads half, probability of tails half, and the total entropy in this coin toss experiment is a half times log of a half minus another half times log of a half with a minus sign out front. All of this equals 1. What does that mean? That if you toss a coin, you get 1 bit of information. And actually, entropy is measured in units of bits. And this is where bits were invented. And that makes perfect sense because a coin is just like a binary value, 0 or 1. So if you know the result of a coin flip, you get exactly 1 bit of information. This is what entropy talks about. Whereas if you have fair dice, then you get 2.6 bits of information. Therefore, it has more entropy and more surprise. This also makes sense with the example of the Gaussians. In a Gaussian, you would expect Gaussians that have larger standard deviation to have more entropy. And this is an analytic formula for the entropy of a Gaussian. And you see that right inside here is this sigma, or standard deviation. And so this value increases as you increase the standard deviation. When you think of a random variable, you want to think of entropy as a measure of spread. It's a little bit like variance is a measure of spread, but variance is very sensitive to scale. So if I took this range up and I broke it up and shifted them so they're at different scales, entropy wouldn't care, but variance would. And because it's in units of bits, what it's actually telling us is how many bits are needed to represent the outcome of an experiment where we measure a variable that's spread like this variable. From entropy, you can also get another quantity called conditional entropy. Now this involves 2 variables. This means you have one variable y and another variable x. Now what we're actually trying to see is if we know something about x, if we can say x is in this range right here, does the amount of uncertainty or the spread of y decrease or increase? So first off, you might be able to say it can never increase because y has whatever spread it has, and no matter what the value of x is, this range won't increase. But it almost always decreases. The reason is because if you look at smaller ranges of x, then you have smaller ranges of y. And that means that knowing x gives you information about y. This is getting towards mutual information. But to get there, we have to understand this idea of conditional entropy, which means what is the spread of y when you have a value of x. So as I said, conditioning can never increase it. So this quantity, which is called h of y given x, is always less than or equal to h of y, which is the entropy of y. And just remember, mutual information is always written as h of some variable. So the exact definition of mutual information is actually pretty simple. It's the overall entropy of the variable minus the new entropy of the variable, which is the conditional entropy of that variable given another variable. So the amount of information that x has about y is equal to the entropy of y minus the conditional entropy of y given x. Now this is a symmetric quantity, so you could interchange the values, you could interchange the positions of x and y and you'll get the same results. So you could substitute in here h of x minus h of x given y, and it would give you the same quantity back. Mutual information and entropy can be sort of visualized like this. So this is the total amount of information that there is in x. That's the entropy of x. Entropy of y. This is the remaining entropy of x once you know y. And this is the remaining amount of entropy of y once you know x. Mutual information is looking at how much information is in between here. So it's the h of x minus h of x given y, or symmetrically h of y minus h of y given x. And this intersection of information, or the mutual information, is really what this is measuring. And this turns out to be a really important quantity because it's much more powerful than something like correlation, because it's agnostic to shape and scale. So it can pick out relationships that have non-monotonic shapes, that have squiggly shapes, pretty much any shape as long as there is a relationship. Here's an example of how you actually compute it from data. If you actually have these data points, then you usually bin them. And this gives you a discrete measure of entropy. So here we've taken the x and y values and we've binned them. And what we're going to count is the probability that your x falls into each of these bins. And then in order to compute entropy, what you do is you compute h of y minus h of y given x at each of these bins weighted by these probabilities, and you sum them up. So in particular, most of the valuation of mutual information is actually coming from this bin because this bin occurs most frequently. And so mutual information is something that can be computed from the joint density of x and y. The overall entropy of y is just given by the p log p formula applied to these bins, negative p log p formula, applied to these bins and summed up, and the conditional entropy is given by restricting to one of these bins and looking at the new entropy. Here, the entropy of y in this bin is actually not restricted that much, but if you go to some of the other bins, it's less than its full range. So this will give you some mutual information, but not a lot. So this mutual information is actually kind of low. It's 0.13, and the reason is because this bin didn't actually decrease in entropy with the knowledge of x. So examples of trends with high and low mutual information. If you have something that is independent, so it doesn't matter what the value of x is, the values of y are pretty much the same, or the values of y pretty much take on the same range, then knowing x doesn't really decrease the variance of y. And so that's not going to have high mutual information. It's going to be the same entropy whether you condition or don't condition, and that's going to give you a low value. On the other hand, if it's the value of y is kind of noisy, but it still kind of jumps around totally independent of x, then it's the same thing. The range is high to begin with, but binning based on x isn't really decreasing those. So again, this is low. High mutual information occurs when y usually has a wide range to begin with, and knowing where in the x it falls actually decreases this spread by quite a bit. So if you knew x was here, y with certainty takes on this value. If you don't know where x is, y could take on this whole range of values. And these are types of trends that have high mutual information. Another definition of mutual information, which you can actually derive with a little bit of algebra from the entropy-based definition, is actually that it's a way of using entropy to compare the joint distribution to the marginal distributions. And so here, instead of the straight entropy, which would be p of xy times log of p of xy, you're looking at p of xy times the log of the ratio. And that's another way of looking at mutual information, but I usually find it a little bit more intuitive to look at the entropy definition. Some interesting properties of mutual information. One is a data processing inequality. So not only can you find variables in high-dimensional data sets that have mutual information and therefore some kind of relationship, whether it's linear or non-linear, you might be able to find more direct and more indirect relationships. Usually as variables are usually going through a noisy channel. So if there's a gene interaction relationship here, there's some noise in how the value of this gene gets translated to the value of this gene. And now if this gene, again, regulates this other gene, there's noise again. So usually what that means is that the mutual information between Y and Z is going to be greater than the mutual information between x and z. So if you have these kinds of variable relationships where y has mutual information with z and x has mutual information with z, you could actually use the value of the mutual information to kind of figure out that this has a more direct relationship. But mutual information is pretty hard to use in more than 2 dimensions. Conditioning on a third variable can increase or decrease the mutual information between 2 variables. So usually it is used 2 variables at a time.